Good morning, everyone. So, welcome to my YouTube channel, Math Program. So, today we are going to see 10th lecture on Riemann integration. So, let's start today's session. So, today we start with the following result. Let f close interval AB to R be a bounded function. Bounded function. Then the lower integral, the upper integral fx dx is equal to limit norm p tending to 0 UPF and lower integral a to b fx dx is equal to limit norm tending to 0 LPF. Okay. So let's see how it works. Let's see its proof. We know that UP upper integral is a to b is infimum of UPF. P is a partition of closed interval AB. Okay. Okay. Now, if Q contain in P contain in Q, then QF is less than UPF. Therefore, the sequence UPF P is a partition P is a partition of AB, partition of AB is monotonically decreasing sequence. Okay. So this is monotonically decreasing sequence. Decreasing sequence. Now, okay. So one thing you also write here. So one more thing you write here. If P contain in Q, then norm of Q is less than norm of P. Okay. And UQF is less than UPF. It means this is a monotonically decreasing. It is not a sequence. This is monotonically decreasing with respect to stat inclusion. Okay. set inclusion. Now we can apply here monotone convergence theorem. Okay, using the same technique as we do for monotone convergence theorem, this sequence then norm tending UPF will converge to infimum. Okay, infimum. Because once we prove monotone convergence, if a sequence is monotonically decreasing and it is bounded below, then it is bounded below, then it converges to infimum. Okay. Now this is bounded. This is monotonically decreasing, and bounded below by bounded below by bounded below by lower integral. Okay, it is bounded below by or you can say directly. Okay, so it is bounded below by this, bounded below by this lower integral, because we always have this one, a to b fx dx always UPF for any partition P of AB. Now by monotone convergence theorem, because this UPF set is bounded below and it is monotonically decreasing, by monotone convergence theorem, by monotone convergence theorem, we have limit non P tending to 0 UPF is equal to infimum of UPF P is a partition of AB. Okay, but this is nothing but upper integral. Okay, so this implies upper integral a to b fx dx is equal to limit this tending to 0 UPF. So we have proved it. Okay. Okay. Now, similarly, what is upper integral? Sorry, lower integral. Lower integral is a to b fx dx is equal to supremum of LPF P is a partition of closed interval AB. Okay. If P contain in Q, then the norm of Q, is less than equal to norm of P, and LPF is less than equal to LQF. Therefore, LPF P is a partition of closed interval AB is increasing. Is monotonically increasing. Monotonically increasing and bounded above by upper integral a to b fx dx, because LPF is always less than equal to upper integral for any partition P of AB. Okay. By monotone convergence theorem, we have, so this sequence, this is a set which is monotonically increasing with respect to set inclusion. Okay. And it is bounded above by monotone convergence theorem. By monotone convergence theorem, we have limit non-p tending to 0, LPF is equal to supremum of LPF P is a partition of closed interval AB. Okay. But this is nothing but upper integral. Sorry, this is lower integral. This is lower integral. Okay. So this implies lower integral is equal to limit non-p tending to 0 LPF. Okay, so this is also. So this result is done. Now move to next theorem. So this is Archimedes C is this. Archimedes-Riemann Theorem. What is this theorem? Let F closed interval AB to R be a bounded function. Then F belongs to R AB if and only if limit norm P tending to 0 UPF is equal to limit norm P tending to 0 UPF is equal to Riemann integral of this. Okay, let's prove this theorem. So let me write it properly. Okay, so we have not written it properly. Next line we can write it. Okay, no problem. So this is a very important theorem. If and only if, okay, if and only if limit non P tending to 0 UPF is equal to non P tending to 0 LPF is equal to Riemann integral of F. Okay, let's prove it. So let's prove it. Okay. Proof. First, assume that F is Riemann integrable. Okay. Then A to B fx dx is equal to upper integral is equal to lower integral. By proposition we have done, by this proposition which I have just proved here. Okay, this proposition. What will be the UPF? By proposition we have UPF is equal to limit upper integral is equal to by proposition we have limit non p tending to 0 UPF is nothing but upper integral, but function is Riemann integrable, so this will be equal to this. And what is limit of LPF when non tending to 0? Limit non p tending to 0 LPF but function is Riemann integrable, so this will be equal to this. So therefore limit non p tending to 0 UPF is equal to non p tending to 0 LPF is equal to upper integral a to b fx dx. Okay, so it is done. First direction is done. Now conversely assume that conversely assume that limit non p tending to 0 UPF is equal to limit non p tending to 0 LPF is equal to a to b fx dx. Okay. So in theorem, you made a correction. What is that correction? You made a correction. It requires some correction. Okay. Correct it here. So in this, you made this one. You skip this part. Okay. So I would like to correct this here. What? I would like to correct this here. It requires some correction. So f is Riemann integrable if and only if limit non p tending to 0 UPF is equal to non p tending to 0 LPF. Okay, both are equal. Okay, if f belongs to RAB, then limit non p tending to 0 UPF is equal to non p tending to 0 LPF. Both the limits are equal and they are equal to in Riemann integrable of this. Okay, Riemann integral of this. Okay, so this is the result actually. CF. Okay, So first we will prove this theorem, and if f is Riemann integral, then this limit happens. Okay. So first assume that f is Riemann integral, then this happens. By proposition, we have this one. Okay. So if f is Riemann integral, we have proved that they are equal, and they actually integral is this. First direction is done. Okay. And if r is Riemann integrable, this part is also done. If part is also done. Okay. Now conversely, assume that this happens. But LPF is less than equal to lower integral. It is less than upper integral, and it is less than UPR. So letting norm p tending to 0, we get what we get? Limit norm p tending to 0, LPF is less than, because this is a constant, this will remain as it is. But these two are equal. So what does it mean? Since limit non p tending to 0, UPF is equal to limit non p tending to 0, LPF by sandwich theorem. We get what we get, because last these two are equal, so inner things will be also equal. Okay. We have lower integral will be equal to upper integral. Okay. So this implies f is Riemann integrable. Okay, done. So this theorem is done. Archimedes-Riemann theorem. Now move to next theorem. Let F1 and F2 belongs to Riemann integrable set. It means they are in. Then F is equal to F1 plus F2 also belongs to RAB. Okay. And Riemann integral of F is equal to sum of Riemann integrals of F1x and F2x. Okay, let's prove it. Proof. Let's put Let P is equal to A x naught x1 x2 xn is equal to B a partition of closed interval AB. Okay. Put Mi dash is equal to supremum of f x f1 x x belongs to this subinterval xi minus 1 to xi. Okay. M capital Mi double dash is equal to supremum of f to x x belongs to this interval. Okay. Small m mi dash is equal to infimum of f1 x x belongs to mi double dash is equal to infimum of f2 x x belongs to xi minus 1 to xi interval. And you know what is capital M? Capital M is capital Mi is equal to supremum of fx x belongs to xi minus 1 to xi. Okay. So we have this one. Now observe that because f is equal to f1 plus f2. Okay. So what is this? This will be, so this implies fx is less than, okay, mi dash plus mi double dash, and that is less than mi dash plus I double dash for all x belongs to xi minus 1 to xi. Okay. So this implies mi dash plus mi double dash is less than mi, and mi always less than capital Mi, and this is less than for all I goes to 1 to n. Okay. Because what is supremum? Supremum is least upper bound. That is why capital Mi is less than mi dash plus mi double dash. And what is infimum? Greatest lower bound. So greatest lower bound will be greater than any lower bound of f. What is the lower bound of any? There is some lower bound mi dash plus mi double dash, small mi dash plus small mi dash. So small mi will be greater than this mi dash small plus mi double dash small. Okay. So multiplying both the side by multiplying both the sides both the sides both the sides by delta xi, we get mi dash delta xi plus mi double dash delta xi less than mi delta xi mi delta xi that is less than capital mi dash delta xi mi double dash delta xi. Now taking sum for I goes to 1 to n, we get what we get. Now we are taking sum both the sides. Okay, so it will be this. So this is I goes to 1 to n mi double dash delta xi. This is double dash. Okay. Now what is this? What is this? This is LPF1. And what is this? Plus LPF2. And what is this? LPF. And what is this? UPF. What is this? UPF1. And what is this? UPF. Okay. So this implies LPF1 plus LPF2 is less than LPF. This is less than UPF. This is less than UPF1. And this is less than UPF2 for any partition P of closed interval AP. So let's say this equation number 1. Okay. Now, since F1, F2 belongs to R. Okay. Then given epsilon greater than 0 by theorem by theorem 1 of theorem 1 by theorem by theorem 1 of Riemann integration lecture 8 we have there exists there exists there exists okay. So first you write F1 here. Since F1 belongs to Riemann integrable set, F1 is belonging to this set. Okay. So F1 is Riemann integrable. So by theorem 1 of lecture 8, there exists a delta greater than 0 such that U P1F minus L P1F is less than epsilon by 2 for any partition P1 of closed interval AB with norm of P1 less than delta. Okay. Okay. Similarly, for F2 belongs to R because F2 is also Riemann integrable. We have U P2 F2 minus L P2 F2 is less than epsilon by 2 for any partition P2 of closed interval AB with norm of P2 is less than delta. Okay. Okay. Now put now let P1 and P2 be partitions of closed interval AB. Okay. Put P is be partitions of closed interval AB. Okay. So we can write this here directly. Okay, one thing I would like to write. You do not write too much things. You directly do here one thing. Hmm. Actually, directly write here. So we directly write here. Okay, no problem. So F1 and F2 both belonging to. It will be better actually. F1, F2 belongs to R. By theorem 1, they exist. Okay. Okay. Norm of P less than del UP F1 minus LP F1. Okay. Less than epsilon by 2 and UP F2 minus LP F2 less than epsilon by 2. By theorem 1 of lecture 8. Okay. So this happens. Now by equation 1, what we have? By equation 1, from 1, from 1, we have, what is this LP1? Sorry, LPF1 here. Plus LPF2 less than LPF, that is less than UPF. Okay, that is less than UPF1 plus UPF2. Okay. Now this is less than this, and this is greater than this. So this implies UPF minus LPF. The difference of UPF with LPF will be less than equal to UPF F1 plus L UP F2 minus LPF1 plus LPF2. This. So this implies UPF minus LPF is less than equal to UPF1 minus LPF1. Okay. Plus UPF2 minus LPF2. Okay. But this is less than epsilon by 2. Okay. And this is also less than epsilon by 2. This is also less than epsilon by 2. So we have that is epsilon. So this implies UPF minus LPF. Okay, less than epsilon for any partition B of closed interval A. Okay, with norm less than with norm of P less than delta. Okay, so by again theorem 1 of Riemann integration lecture lecture 8, we have F belongs to R A B. Okay, now by, so we have shown that F is Riemann integral by again by equation 1 we have LPF1 plus LPF2, that is less than LPF less than UPF less than UPF1 plus UPF2. Okay. So letting non-P tending to 0, we get by proposition. What we get? Letting non-P tending to 0 by proposition of this lecture, we get so what will be this? So limit non-P tending to 0 LPF1 plus limit non-P tending to 0 LPF2, and that is less than limit non-P tending to 0 LPF, that is less than non-P tending to 0 UPF, that is less than limit non-P tending to 0 UPF1 limit non-P tending to 0 UPF. So now, because function is Riemann integral by proposition, what is this? This is A to B F1x dx. And what is this? What is this now? A to B F2x dx. Now what is this? This is equal to a to b. When we have function Riemann integral, this will be nothing but this limit non-p tending to 0 LPF and non-p tending to 0 UPF will be same. So I am writing only this one. This is less than this one. A to b f1 x dx plus a to b f2 x dx. Okay. Now we have this one same and this one is also same. So what does it imply? The middle thing is equal to, because lower is this, upper is this. So this implies a to b fx dx is equal to a to b f1 x dx plus a to b f2 x dx. Okay. So this theorem is also done. So we have proved that if f is Riemann, f1 and f2 are Riemann integral over AB, f is equal to f1 plus f2 is also Riemann integral. And Riemann integral of f is nothing but Riemann integral of f1 plus Riemann integral of f2. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. We will see you in next class. Thank you very much.